Hello, calculus students. Hydrostatic force is the amount of force exerted on a surface that has been submerged in a liquid. A little review on fluid pressure. If you have a tank of a liquid, then the amount of pressure all along the bottom edge of it remains constant because the bottom edge of it is at the same depth. And as you might know from, say, scuba diving or snorkeling, or even just going to the deep end of a swimming pool, when you dive down, you notice that your ears start to experience some pain and discomfort. That's due to fluid pressure. The deeper you go into a liquid, the more pressure is exerted on your body. This is also true for gaseous fluids like our atmosphere. When you're looking at the sides of a tank, the further you go down the sides of a tank, the more force is being exerted because of the increasing pressure as you go down. That's what these little arrows that you're seeing here are representing. The length of the arrow can be thought of as how much force is being exerted. And so there's very little force to none near the top exerted by the liquid, but the further down we go, we get more force exerted. So the amount of force being exerted on the side of the tank, the pressure changes as you go down, so you have more force towards the bottom than you have the top, and you have this gradual, continual change as you go down. You're going to need integrals to figure out how much force is exerted on a side on a plate that's vertically submerged in liquid. You would not need an integration to determine how much force is being exerted on a horizontally submerged plate, because if the entire plate is at the same depth, then the entire plate is at the same pressure level. Pressure is a unit of force per area. So when you multiply that by area, you do get total force. For example, near the surface of the Earth, the atmosphere exerts 14 pounds for every square inch. And so if you were to have a 3 square inch surface, would it be experiencing 42 pounds of force exerted on it? Now, fluid pressure is a function of depth, and the pressure at a certain depth is found by doing the product of the weight density times the current depth. Now we're going to use a symbol. It looks like a W. It's actually a Greek letter omega, and it's a constant for every liquid. And then the depth, we'll use D for depth. So if the weight density is 62.5 pounds per cubic foot, and that's how much water weighs, that's its weight density. We're talking specifically about water. Other liquids would have different weight densities. Or in the metric system, it's 9,800 newtons per cubic meter. Say, what's the pressure at 3 feet deep in water? Well, you would take the weight of water per volume per cubic foot, multiply it by how far down you are, which is 3 feet, multiply the two numerals and you get this 187.5, and multiply the two units, you will notice that you get a feet over a feet cubed. The arithmetic of units leads to per square foot. And so at a depth of 3 feet, we wind up with a unit that makes sense for pressure, force per unit of area. Okay, so let's say we have a plate that's been submerged vertically. Here's our plate, we're looking straight at it. We'll say this is the top of the water up here. I'm going to choose to do all of our problems here using the y-axis going straight up, which means that the bottom of our plate is going to be at a lower y-coordinate. We'll call it y equals a. And the top of the plate we'll say is at a higher y-coordinate, y equals b. And we're going to slice through this plate horizontally. And the reason we want to do horizontal slicing through this region is because if you take any one horizontal slice like that one, then that entire slice is effectively at the same depth. Therefore, the pressure exerted on this strip here is going to be constant. If you do vertical strips through your plate, then you have more and more and more and more intense pressure down here. And so you're going to need an integral just to figure out how much force is on that strip. We don't need an integral within an integral. If we do horizontal strips, then any one strip that you draw here is going to be at the same depth, hence the same pressure. So I'm going to draw an arbitrary strip through here. It's going to have a thickness of dy. It's going to have a length that we're going to call L, and it's going to be at a certain depth that we'll call D. So we want to compute how much force is on that strip, and we simply have to say, well, what's the pressure at the depth, and then times the area of the strip. If your pressure is constant, you just have to multiply the constant pressure times the area, and you get the total force on that strip. So our basic setup for all of these hydrostatic problems are going to be integrals of the structure. This is not saying dA. This is not a differential, by the way. This d is a depth. And the omega times d is the weight density times the depth. This is the pressure. And then, of course, we then multiply it by the area. And in this case, the area of our strip is the length of the strip times the little thickness dy. And then these would be y coordinates. So you could rewrite this integral in the following way, that the total force will be an integral from y equals a to y equals b, omega dl dy. Omega will always be some constant. It depends on which fluid we're working with and what system Are we in metric or US? The d and the L are typically functions of y. And then, of course, we have the differential dy. The reason I'm calling d and L functions of y is as you imagine different strips, starting at the bottom strip, then going up to the top, the length of the strip is clearly going to change, but then so will this value here, because not all the strips are at the same depth. When you multiply the omega times the d times the a, all of that is the force on one strip. And then you do the integral right here, and that adds them all up, and you get the total force on the plate, which is what we're after. And so answers here will be in units of force, which will be either pounds or newtons, depending on which system we're working with, metric or US. Okay, as our first example. A triangular plate is vertically submerged into water, as depicted below. The top edge of the plate is 1 foot deep, and we know that the top edge is 4 feet long. The bottom tip of the plate is 6 feet deep. That's 1 foot, but from the top edge of the plate down to the bottom tip is 5 feet, because this tip down here is 6 feet deep. Find the total hydrostatic force pressing on one side of the plate. All right, so I'm going to draw an arbitrary slice through here. We're going to want to figure out what the length of that slice is, and then also an expression for what the depth is of that slice. Now, in order to do this, we need to put a frame of reference into play. The recommendation in step 1 is, that should be the word plate, not container. So draw a side view of the plate and position the center of the bottom at the origin. This is suggesting that we have the x-axis down here at the bottom. And I'll put the tip here is where the origin's at. So we have a y-axis. Now, because the x-axis, its equation is y is equal to 0, the top of the water would therefore be at location y equals 6, and the top of the plate would be at y equals 5. You integrate from the bottom of the plate to the top of the plate, not to the top of the water. So we're going to integrate 0 to 5. If I had made my frame of reference somewhere else, then all my y-coordinates would change. And you can do that. There's lots of freedom actually in setting these problems up, but to be consistent, I'm going to try to always put the bottom of the plate centered at the origin and then try to model from there. Step 2 is find the length of the slice as a function of y. There's several ways you might go about doing this. You could figure out the equation of this line right here and figure out the equation of that line right there. But since I don't exactly know how this 4 is split amongst the top, it's kind of hard to find those equations. So maybe that won't be a very effective approach. However, you should be able to reason that L will change in a linear fashion, because it's between two lines, and so as y changes, L should grow in some linear fashion. With that in mind, you can make a little table of points and determine the linear relationship between them. So when y is 0, when you're at the bottom of the plate, the very first strip down here at this tip down here, what is its length? Well, its length is going to be 0 down there. But by the time we get to y equals 5, how long is the strip up here at the very top? And that's where that 4 comes into play. And because we expect a linear change in L as y varies from 0 to 5, we can do point slope form. So I'm going to find the slope. And when I say slope, I'm not referring to the slope of this line or some other line in this image. I'm referring to if you plotted this data, y against L, and you had 2 points, I'm trying to find the slope of that line. All right, so the formula, we do the change in the L coordinates. So we say 4 minus 0 divided by the change in the y coordinates, 5 minus 0, then we get 4/5. Well, in this case, L is the dependent variable and y is the independent variable. So this is our general structure. And you can use the 0, 0 point as your L1 and y1. So in this case, it winds up being, and this gives us the formula for L as a function of y. Let's test it. Plug in 0 for y. What L do you get? You get 0, which is what you would expect. Plug in 5 for y. What L do you get? You get 4, which is what you would expect. And then if you plug in some intermediary y, like y equals 2, then you're going to get some L that's somewhere between 0 and 4. It's going to be the length of the strip that you see in our image over here, depending on what height that we're at. Step 3 is to then express the depth of the slice as a function of y. Because we've situated the x and y axes in this, we have a frame of reference at the current height of the strip that you see right here, that is at a height that we call y. So if you know that from the x-axis to the top of the water is 6, and you should reason that the depth is a simple 6 minus y. Keep in mind that our strips are going to start down here at y equals 0, and when y is 0, the initial depth should be 6. Right? That's the depth of the strip. And by the time we get to the top, when y is 5, the final depth should be 1. You could, in theory, do the same thing we did up here with, you could create a y depth table and do an equation. Okay, so once we find the depth of the slice as a function of y, we can create the integral that would give us the total force. So this is going to be an integral from 0 to 5. The omega, let's see, what liquid is this? This mentioned into water. And notice everything's measured in feet. So we're going to wind up using this value for the weight of water. All right, so we have omega 62.5 times the depth. The depth is 6 minus y times the area. L times dy will give us the area of that strip. 4/5 of y, and then times the dy is the thickness. Now let's dissect this and see what each piece is. When I do the units, this is pounds per cubic foot. The depth is measured in feet. The length of the strip is measured in feet. And the differential is measured in feet. And so when you multiply all these units together, you get pounds, which is what we're looking for. How many pounds total are on this plate? Looking at the combinations of these things, right here is the pressure. This component here is the area. Pressure times area is what gives you force. Now, I did this on the calculator, and I got 5,000 thirds, which is approximately 1,666.7, and the unit here would be pounds. Okay, let's go to the next one and follow the same 3 steps. A semicircular plate is vertically submerged and the water is depicted below. The top edge of the plate is 3 meters deep and 4 meters across. Find the hydrostatic force pressing on one side of the plate. And when I say pressing on one side of the plate, so here's your water and this is a diagonal view of the plate. Here's the amount of force pressing on one side. Now, technically the amount of force is pressing equally on the opposite side. That's why the plate doesn't move anywhere, but we're just calculating how much force is pressing on one side. So what if this is the wall of a dam? And so the water actually ends here and you only have water pressure from this side. I didn't want that expression pressing on one side of the plate to be a source of confusion. Let's do the frame of reference first. I'm going to situate this so the bottom of the circle is on the x-axis and the y-axis is going to go right up through the middle of the plate. Now we're told that the top edge of this plate is 4 meters across. So that tells you what the radius of this circle is. The radius has to be 2. So the top edge of the plate has to be y equals 2. And we also are told that the top edge of the plate is 3 meters deep. So that means the water level is at height y equals 5. And we have our frame of reference in play. The next thing we do is draw an example of an arbitrary strip through here. We got to figure out how long it is. Its thickness will be dy, but then we also have to figure out how deep it is as functions of y. Now, reminders about working with circles. If I say x squared plus y squared equals some number squared, like 4 squared, so equals 16 in other words in this case, you get a circle centered at the origin whose radius is 4. If you want to change the radius and change that 4, let's say you want the radius to be 3, so you can just put a 9 here, 3 squared, and now you have a radius 3. If you want a radius of 2, you put a 4 there. Now, our circle has diameter of 4, radius of 2, so this is the equation I want to work with. However, notice that the bottom of it is not at the origin as depicted in my image here. If you want to shift a circle up, then you replace all the y's with y minus a number, and that'll move the circle up. If you want to shift down, then replace y with y plus a number. Notice where our circle is at. We want to shift our circle up so that the bottom of the circle is at the origin. So then we want to shift our circle up, so replace y with y minus, and we need to go up 2 units, and that should get the circle where I want it to be. If you want to move circles left and right, then leave y, replace x. If you do x minus a number, like x minus 3, it's going to shift the circle to the right 3. If you want to shift a circle to the left, then do x plus. So the one that we want definitely, though, is this one right here. Let me draw just a tiny little image down here. Now what we're going to do is we want to figure out how long this strip is as a function of y. That tells me I need to figure out what the equations for the right side and the left side of the circle are in this picture. These lengths are horizontal, so they're x coordinates. That tells me I need to solve this equation right here for x, and that's going to give me the left and right sides of this circle. So when I solve for x squared is equal to 4 minus, and then y minus 2 squared, and then take a square root. And so we get plus or minus. If you keep the plus, you're going to keep the right side of the circle. If you keep the minus, you're going to keep the left side of the circle. Okay, so that's how you break the circle apart into functions of y, the right side and left side. If I say x equals the square root of 4 minus, and then parentheses, do y minus 2 and parentheses squared, notice that we just have the right side of this same circle. But if I put a minus sign in front of here, we have the left side. Okay, that's the key to working with this circle. This time we're working with water, but notice that everything's given in meters, so that means that we want to work with the metric system. So we're going to be using this value for omega, 9,800 newtons per cubic meter. If you want to figure out how long the strip is, then you do right function minus left function. Well, the right function is the green, and we're going to subtract from that the left, which is the negative of the square root of the same thing. which really means you just add those together, by subtracting a negative, and you wind up getting 2 of these square roots, which makes sense symmetrically, because if you only do one of them, if you figure out how far across it is from y-axis to the green, and then just double that to get the whole thing, then you get all the way across. When you're at y equals 0, then your strip is down here, its length should be 0. Well, plug 0 in for this y and see what L you get. You get 0 minus 2 is negative 2, square that's 4, subtract it from 4 is 0, square root that is 0, times 2 is still 0. So you do get L equals 0. It confirms the correct L at the bottom. By the time we finish our integration at y equals 2, which is where the plate ends, plug 2 in for y, do 2 minus 2 is 0, squared is 0, subtract from 4 is 4, take the square root of that's 2, and then double that's 4, and that does confirm that the L is 4 units across at the top. When you plug in 0 for y, you get 0 for L. When you plug in 2 for y, you get 4 for L. Now, this is not a linear function, unlike the other example, but it is the correct function that does at least confirm the endpoints. Okay, now we're ready to set up our force integral. We're going to integrate. The first slice is going to start at y equals 0, the bottom of the plate, and the last slice will be at y equals 2, the top of the plate. We're going to have 9,800 as our omega, times our depth. Keep in mind that the distance from this slice to the x-axis is the y-coordinate. And since the bottom of the plate is 5 meters deep, so that means d is going to be 5 minus y. So our depth is 5 minus y. Our length is this 2 times the square root of 4 minus y minus 2 squared, all in square root. And then the thickness is the dy. So once again, the units here are newtons per cubic meter. The depth is measured in meters. This double thing is measured in meters, and the differential is measured in meters. So you're going to get newtons out of all this. And there's your pressure, and here's your area component. Reach for the calculator. You're going to get 236,992.3, and the unit here is newtons. Okay, we just have one more to do. And this time our plate is part rectangle, part semicircle. And we're not in water any longer. We're in an oil that weighs 8,000 newtons per cubic meter, so a little bit lighter than water. Let's get the frame of reference. Let's put the x-axis right down here at the bottom. So that's y equals 0, in other words. Put the y-axis right through the middle of this. The highest point of the plate is 2 meters deep. Okay, so that tells us that this gap right here is 2 meters. The bottom edge is 8 meters across and 8 meters deep. Okay, so that tells me y equals 8 is the top of the water, which means y equals 6 is at the top of the plate. It says the bottom of the edge is 8 meters across. So that tells me that's 4 and that's 4. We're going to split this up into a rectangular portion and a semicircular portion. The radius has to be 4, so that's 4, which means that this is 2. We're going to split our integral at y equals 2. We're going to actually have to do this in 2 different integrals because of the 2 different shapes involved. So we have the rectangular part. We're going to figure out what that one is, and we'll call that force 1. And then we're going to have force 2 on the semicircular part. And the reason is because we have to do a switch of functions for determining the length. So let's do force 1. The nice thing about force 1 is that when you draw a horizontal strip across here, imagine the strip starting there and then finishing right there, that the L isn't changing, right? The length of the strip is always constant, at least for this part of the plate. So for force 1, let's get all the pieces here in place. We have omega d L dy, and for force 1 we're going to start at y equals 0 and end at y equals 2. The omega is now only 8,000 newtons per cubic meter. That's the depth. Well, the strip I've drawn currently is y units above the x-axis, so the depth will be 8 minus y. The L will always be 8, and then times the dy. So here's our integral that we would set up to get the first force, and that winds up being 896,000 newtons. Okay, force 2 on the semicircle. I'm going to draw an arbitrary strip. Right here is length L, and its depth is d. Right, this length here is still y. So depth is still 8 minus y. Our limits of integration are going to change as well. Force 2. Well, that plate starts at y equals 2 and ends at y equals 6. The omega is the same. It's still 8,000. The depth is still 8 minus y. And it's the length that's going to be the problem. So we're going to want to do a circle whose radius is 4. So we have x squared plus y squared equals 16. But we need to shift it up so that the center has been shifted up 2 units to this point right here. So to shift it up, we're going to have to replace the y with y minus 2. And then in order to get the right side and the left side as separate functions of y, we're going to have to solve this equation for x. So that's going to give me x equals plus or minus the square root of 16 minus y minus 2 squared. And then when I do right minus left, we're going to wind up getting that the L is twice this radical. That needs to go in right here. We have twice times the radical of 16 minus y minus 2 parentheses squared, all in the radical, and then the dy. And when I reach for the integral calculator, that gives us approximately 865,038.2 newtons. And then the total force, you just add these individual forces. And so we're going to get a total force of about 1,761,038 and then 0.2 newtons. Okay, and that is all the examples we need to see for doing hydrostatic force on a vertically submerged plate.